This week on the show, we cover encrypted crash dumps in FreeBSD, a bit more on time on Unix and its various forms, the improvement of ZVOL sync write performance with the taskq. We cover a tutorial part 1 with the central log host with syslog-ng. Then we cover the NetBSD Entropy Overhaul and setting up a NetBSD kernel development environment and much more in this week's episode of BSD Now. BSD Now, episode 349, Entropy Overhaul, recorded on the 6th of May 2020. Hello, I'm your host, Benedikt Reuschling.
And I'm Alan Jude.
Welcome back. Hope you're safe at home or all in good health as this episode finds you. And we have, of course, a nicely prepared and filled show for you. And this is the headline today, EKCD, Encrypted Crash Dumps in FreeBSD.
So this is over on Mariusz Zaborski's blog, and it says, some time ago, I described how to configure network crash dumps. In that post, I mentioned that there is also the possibility to encrypt the crash dumps. Today, we will look into this functionality. Initially, it was implemented during a Google Summer of Code project back in 2013 by our mutual friend Konrad Darsky. Sorry, I butchered your name. Who made it available as part of FreeBSD 12. If you can understand Polish, you can also look at his presentation over from the BSD PL user group, on which he gave a comprehensive view of all of the kernel crash dump features and so on. The main issue with crash dumps is that they may include sensitive information available in memory during a crash. They will contain all of the data from the kernel and the userland, like passwords, private keys, etc., anything that was loaded in memory. While dumping them, they are written to unencrypted storage, so if somebody took the hard drive out of that machine, they could then have access to that sensitive data. If you are sending a crash dump through the network, it may be captured by third parties and so on. Locally, the data is written directly to a dump device, skipping the geom subsystem. The purpose of this is to allow the kernel to write a crash dump even when it's in its panic state. And maybe the panic occurred in the geom subsystem, so you can't count on geom being there because it might be what has crashed. Same reason why crash dumps in ZFS are an issue. It means that a crash dump cannot be automatically encrypted using Geli, which is a geom class. To protect your privacy, you should encrypt your crash dumps, and FreeBSD Now offers that as a possibility. The functionality is called EKCD, or Encrypted Kernel Crash Dumps. The idea behind it is that the administrator or security officer at your company will generate an RSA public key, or RSA key pair. The public key is provided to each machine, so when it crashes, it can encrypt to that key, but only the person with the private key will be able to read it. So when the key is loaded, the machine uses it to generate a one-time AES key, which is used to encrypt the actual crash dump. The AES key is then also encrypted using the RSA key and stored on the machine as well. This way, only the owner of the private key can decrypt the AES key, which they can use to decrypt the crash dump. Because encrypting the whole crash dump with RSA would be really expensive and run into limitations, whereas AES is meant to be fast. Anyway, so the whole crash dump is now protected with the AES key, which is protected with the RSA key. If you're familiar with cryptography, this is a pretty standard practice because of the limitation of RSA keys. Knowing all of this theory, let's look at how you can actually configure a FreeBSD box to do this. First of all, you have to check that your FreeBSD box has the encrypted kernel crash dump feature built in. If you're using the generic kernel, then you should already have it, but if you've customized it, maybe you don't. And so it shows how to use the config command to check your kernel and see if it has the EKCD feature. Then the supervisor or security officer or whoever needs to generate a new RSA key pair. And so that could just be, OpenSSL gen RSA or whatever. Generate that and keep it safe. You may also be interested in encrypting this key itself, since you don't want the decryption key for your encrypted kernel crash dumps lying around unencrypted, because then you might as well not have encrypted the crash dumps. So it shows how to do that. Now you want to transfer the public part of that key over to the machine that you want to store encrypted or generate encrypted kernel crash dumps. And basically, as part of the dump on command, which tells the system which device it should dump on when it crashes, you just have to provide the key. So dump on -k, the path to your key, and then the device you want to write your crash dump to. Now, for testing, we can use the cctl debug.kdb.panic to cause the system to panic and write a crash dump. When the machine comes back up, it should automatically run savecore to save the encrypted kernel crash dump out to a file, and you'll end up with two files. Key.x, which is the AES key needed to decrypt the crash dump, and that's encrypted with the RSA key, and then vmcore_encrypted.x, which is the actual crash dump encrypted with that AES key. Then you just need to use the decrypt core command and provide access to the private key and tell it, hey, using this private AES key, this private RSA key, decrypt the AES key, then use that to decrypt the kernel crash dump, and it will write out a regular crash dump that you can read with KGDB or whatever and debug the problem. And that's about all there is to it. It's actually a pretty nice interface. Basically, on the dumping machine, you have to tell it, here's the public key I want you to save the encryption key to. And then on panic, it will generate a new AES key, encrypt that with the RSA key, and then encrypt the crash dump with the AES key. And then you just run decrypt core when you want, and you can then read the crash dump and debug the problem, but nobody else can read it if they don't have the keys.
Very nice.
Mm-hmm.
Yeah, so thanks, Marius, for another how-to and introduction to this tool. And next up, we have a bit longer article, but nevertheless interesting. Time on Unix, it's called. And it's divided into different sections. So first of all, what is time? Then there is how to represent time. Then where do we usually find time in Unix? So there's a couple places that you probably haven't thought about. Then there's system time, hardware time, and internal timers. The distinction between them is important. Then syncing time with external sources so that you can get the actual accurate time on your machine. And then there is what depends on time and human perception of time.
Yes. Time is this very weird concept. There's a couple of great lines here near the beginning. It's like, in physics, time is the progression of events. Without events, there's no time. It is defined by its measurement, which changes at a specific interval, can be considered a unit, though still infinitely divisible. In physics, there are two ways to view time. In classic physics, time is absolute, independent of the perceiver, synchronized for everyone. While in modern physics, we have Einstein's special and general relativity that applies. Things depend on a frame of reference. Time can dilate or contract with an effect of gravity. We can walk or talk about space-time continuums and so on. Equations work equally well both ways, and the math holds up in the future and in the past. However, the arrow of time in our universe seems to go in a unique direction. Peculiarly, we see that time in computers, unlike in our universe, can actually go backwards at specific events. On one hand, the atomic clock counts time regardless of the events happening around it. And on the other hand, we have this moving planet in space that is subject to other forces, where we've chosen the fact that one full orbit around the sun equals a year, and that one full, approximate, rotation on itself is a solar day. The space between two transits of the sun, the maximum height in the sky, both of these values ought to diverge and differ eventually. The Earth, because of its unevenness and current position in our orbit, could rotate around the sun or itself faster or slower, its speed changing how long a day and a year are, which is really complicated when you're trying to use a computer where time needs to stay, each second should be the same length as the other seconds.
Yeah, it's not so simple as you might perceive it. And so that's the introduction, how that time is defined in like seconds. And then they talk a little bit about UTC. UTC is a version of the Universal Time Standard. In this standard, we also find UT1 that keeps track of Earth's rotation angle using GPS satellites. It is the mean solar time at 0 degree longitude and is a better and more precise version of GMT.
But yes, the Unix way of keeping track of time seems to be pretty elegant. It's the number of seconds since January 1st, 1970. And in particular, it's generally the easiest way to do math. It's, like what's 30 days from this date? Well, you start with converting the date to a number, then you add 30 days times the number of seconds in a day. And now if you turn that number back into a date, you don't have to worry about, month rollovers, like how many days are in the month that you just went through and so on. You don't have to do all this complicated ramblings. And it even takes care of time zones, although that one can be tricky. If the time zone changes, is 30 days from today, when the time zone changes between DST and not in the middle, obviously you meant a month from now at the same time. But exactly 30 days from now or 31 days from now is actually an hour earlier there because the time changed.
Mm-hmm.
And yes, that's why it makes sense for the computer to keep track of time in UTC and then keep track of local time as the offset from that, and just know that, okay, we would just take whatever the time is in reality and shift it into your local version of reality.
And then there's the section on representing time, where you have locale and TC data. So they talk a little bit about the different time zone format works. And, what you usually would do is set your locale properly. So there's locale-ck date_fmt, so that you can see what LC time gives you, and the date format like day, month, year, or month, day, year, whatever it might be, hours, seconds, minutes. And the available locales are usually found in user share locale, so you can see that there's different locales available if you want to switch between them or set them in the first place. Usually the installation does that for you, but in case you messed that up, then you can do it on the command line later. Then there is TZ, the TZ POSIX environment variable, which can also be used to specify the zone in human-readable format on the command line, and the TZ-dir to specify the location of the TZ data. That means separate users on a single system can have different time zones. So, for example, you can set TZ to America, in this case, Los_Angeles, and then date, and then you can see the date that's currently in Los Angeles. And if you just type normal date, then depending on your time zone variable, then it will represent a different time zone if it's not the same. And then where do we usually find time on Unix? So there's POSIX time, uptime, time itself, so the time commands, programming languages and timestamps, file system A-time, C-time, M-time, and cron. They talk about each a little bit in that particular section. And yeah, all of these are important in their own manner. And, who hasn't scheduled a cron job to run at a certain hour? And if the clock's not properly working or time in the computer is completely messed up, then this cron job will probably never run. And then they talk about system time, hardware time, and internal timers. So there's the hardware time versus the system and local time. The clock hardware sources and configurations and what they do. Tickers, timers, and their usages are also discussed. So this is another important factor. They also talk about dev_RTC, how Unix represents the clock in everything is a device or everything is a file. And so they talk about that. And as far as I see, the article is fairly Unix agnostic. It's not too specific to any kind of Unix. So they talk basically what most, if not all, Unixes have available.
Yeah, and there's even talk about the special hardware, like the new ACPI power management timers versus the high precision event timers, and a bunch of things of that nature. So if you've ever wondered about time, this is probably more than you wanted to know about time.
Oh yeah, very thorough article, has a lot of details and information, and a very big section at the end about with references if you want to really go much more deeper than this article already is going.
If you are interested in leap years or solar time, or what the apparent mean time of the sun is, or how AIX worked in 1971, there's references to all of it.
Yeah, you can spend a lot of time researching time, turns out. All right, in our news roundup this week, we have improved the ZVOL sync write performance by using a taskq. That sounds interesting.
So this is a change that just went into upstream ZFS. And it says, so prior to this change, any synchronous write to a ZVOL was basically processed serially, meaning one at a time. This commit makes ZVOLs process concurrently all outstanding sync writes in parallel, similar to how reads and asynchronous writes are already handled in ZFS. The result is that the throughput of synchronous writes is at least triple. So when a write comes into a ZVOL, for example, over iSCSI, it is processed by calling the function ZVOL_request to initiate the operation. ZFS is expected to later call the bioend.io function when the operation completes, possibly from a different thread. There are a limited number of threads that are available to call that ZVOL request function, one for each different iSCSI client, unless you're using MC/S or something slightly exotic. Therefore, to ensure good performance, the latency of ZVOL request is important because the whole iSCSI server is going to be blocking on that. So we want many I/O operations to the ZVOL to happen concurrently so that it'll be nice and fast. In other words, if the client has multiple outstanding requests to a ZVOL, the ZVOL should have multiple outstanding requests out to your storage hardware. That is, having multiple concurrent ZIOs in ZFS and requests out to the hard drives underneath. For reads and for asynchronous writes, writes where acknowledge the data before it hits stable storage is fine, ZVOL request achieves low latency by dispatching the bulk of the work, including waiting for that I/O, into a taskq, which is basically threads that go off, do work, and then tell you when they're done. The taskq callback, which gets called when the task is done, such as ZVOL read or ZVOL write, will then block until the work is actually finished. The ZVOL taskq by default has 32 threads and can have up to 32 concurrent IOs to disks in service of those requests from the ZVOL. However, for synchronous writes, where it's a database or something and it says, don't tell me this is written until it's definitely on disk, even if the power goes out or whatever, it was having to call the ZIL_commit function, which if you have a separate log device, we'll end up writing it to that log device first, or if you don't, then it gets written as part of the pool, but in a different area. So normally ZFS writes out data in big batches called transaction groups, and usually about once every 5 seconds or once there's too much data to store in memory. But you wouldn't want your database to have to wait 5 seconds for every transaction in the database. That would take forever. So when it gets one of these important requests, it writes it down somewhere else and makes sure it's safe, and then lets the application know, okay, it's safe, you can continue. And then when that transaction group actually closes, it gets written normally, basically copied from the ZIL to the normal write path. And then once that's done, that ZIL block can be freed and reused later. And so that's what a slog does. And so that's why you wouldn't want every write to go through your slog necessarily, because you would be writing it twice for no reason. So when you get a synchronous write coming in, you call ZIL commit, and the ZVOL request does not use the taskq because it knows it has to wait until ZIL commit is finished. So instead, it blocks while it waits for the ZIL to write data and be complete. This has the effect of serializing the sync writes, since we only have one thread per ZVOL that's going to be calling a ZVOL request. So if we don't return, that thread can't do any other work. So in other words, each ZVOL will only process one synchronous write at a time, waiting for it to be written to the ZIL before accepting the next request. The same issue happens when you have the flush operations, again, because you have to call ZIL commit. So this changes ZVOL request to use taskq dispatch ent for synchronous writes and flush operations. Therefore, we can have up to 32 threads in that taskq simultaneously calling ZIL commit for a theoretical performance improvement of up to 32x, although that's theoretical. To avoid the locking issues described in the comments in the code, when this commit removes those comments because they're worked around, we acquire the range lock from the taskq callback. So when the taskq fires, it calls back into ZVOL write, which waits for it to be finished, but it waits with the lock held for that range of data so that other ranges of data can still happen concurrently. This applies to all writes, both synchronous and asynchronous, as well as reads and any discard operations. This means that multiple simultaneously outstanding IOs which access the same block can complete in any order. This was previously thought to be incorrect behavior, but a review of the block device interface requirements for the different OSs reveal that this is fine. The order is inherently not defined. The shorter hold time for the range lock should also provide a slight performance improvement. For an additional slight performance improvement, we also used the taskq dispatch ent instead of just taskq dispatch, which avoids having to allocate some memory and it eliminates a possible failure mode. This applies to all writes, both sync and async, as well as reads and discards. So some of the performance improvements from this will help everything, not just your asynchronous or your synchronous writes as well. So results, we used a ZVOL as an iSCSI target from a Windows initiator using a single connection. We used the disk speed tool to generate a workload with 4 threads, doing 1 megabyte writes to random offsets in the ZVOL. Without this change, we topped out at 231 megabytes per second. And with the change, they managed to do 728 megabytes per second, which is a 3.15x improvement in performance. We also ran some real-world workloads, like restoring a Microsoft SQL database, and saw throughput go up by at least 2.5% or 2.5 times the original speed. We saw more modest performance wins, typically in the 1.5 to 2x range, when using MC/S, that is basically having 4 concurrent connections to the iSCSI target, and with different numbers of client threads, using 1, 8, or 32 client threads to make sure there was a lot of outstanding I/O going across iSCSI.
Not bad, not bad.
Mm-hmm. When this pulls into FreeBSD, it means, if you're running a ZVOL or a beehive off a ZVOL or using iSCSI, which a lot of people are, they will now get much better performance.
Okay, I will definitely look forward to getting this downstream. Okay, then we have a tutorial for you. This is a 2-part tutorial, so we'll cover the second part next week's episode. So this one is for the introduction, a central log host with syslog-ng on FreeBSD, although I think you can do it on other BSDs as well. So you just replace a couple commands. So here it starts with syslog-ng is the Swiss Army knife of log management. You can collect logs from any source, process them in real time, and deliver them to a wide range of destinations. It allows you to flexibly collect, parse, classify, rewrite, and correlate logs from across your infrastructure. This is why syslog-ng is the perfect solution for the central log host of my, or mainly FreeBSD-based infrastructure. So the requirements at the beginning, to set this up, you need the following. An up-to-date FreeBSD system version 11.x or 12.x. This system is configured as a central host using syslog-ng, so this is where all the logs are collected. For this post, it is assumed that the log host has the IP 10.20.30.101. The log host logs syslog messages for 1 week only, with a separate log file for each weekday, so Monday, Tuesday, Wednesday, and each log file is overwritten after a week. And please bear in mind that other configurations are possible with syslog-ng, so this is just for the example here. The hosts which log to the log host use the FreeBSD syslog daemon.
Right, so you don't have to install different software on every machine, just the machine that you want to collect all the logs on.
Yeah, exactly. So the central server needs syslog-ng. Okay, then they start basically with syslog-ng installation. That's fairly easy. Package install syslog-ng. There's a package, just install it and forget about the rest. Disable syslog-d. So in this second step, you need to shut down the standard FreeBSD syslog daemon and make sure it does not start at system boot. So you run service syslog-d stop and sysrc syslog-d_enable equals no. And then you start the initial configuration of syslog-ng. So to start that, you should let the daemon run at startup. So you run syslog_ng_enable equals yes. So you're switching around the syslog daemon to syslog-ng. And that daemon has a central configuration file called syslog-ng.conf. Very easy to remember. And this lives in user local/etc. Since this is third-party software, it lives there. Base configuration is done first. So what you need to do, it takes care of the base syslog-ng configuration of the host itself only. So just this log host should also collect its own logs. And the configuration part, which makes this host implementation a log host by defining or by being able to receive syslog messages from other hosts, is described a little bit later down this blog post. So you would, of course, read the man page, syslog-ng, man5, syslog-ng.conf, and then start the service, sudo service syslog-ng start, fairly easy, and then check the status. Yes, if there's a PID returned, then this thing is running. Okay, so how do you make this a log host now? there's a last line in the base configuration file that states include userlocal /etc syslog-ng/conf.d. And this is the configuration directory where you read, where syslog-ng reads in its final configuration options. So it reads this config file first, and then with this include line reads from that config directory everything that you put in there. So let's make sure this directory exists first. So you create this one, make dir, or on ZFS, you would do a ZFS create and to, of course, compress this one. But that's what I would recommend because logs are very well compressible. So you save a bunch of disk space. Then use your favorite editor to make a file called loghost.conf in this directory and add a source directive. So there's a syslog directive in there with the source IP and then a transport of UDP. And that's a fairly similar configuration file for the filter syntax as well. So to check that you use UDP port 514 so that it can receive the syslog messages. And then you add a filter, f_all in this case, to filter out all the log levels that you want to have. So in case you want to exclude a couple of things, then you can filter these out or include them.
So for example, they're covering everything from debug to emergency that's not also program devd and levels debug through info to eliminate all the debugging information from devd, but picking up any of the higher log levels from devd or anything from everything else.
Then, as we mentioned, you want to have this configuration to save logs for a week only, and with a separate log file for each weekday, monday.log, tuesday.log, etc. Each log file is overwritten the next week automatically. And be aware that a lot of other configurations are possible with syslog-ng. Just check the man page, and there will be plenty of examples. This one in the blog post has a destination called d_daily and defines basically that there is in /loghost/daily logs, there is a $weekday.log, and this gets replaced with the current weekday. And then you define what the owner of that file should be, in this case, root and wheel. Permissions, of course, for the directory as well. And you want the system to create the directories when necessary.
If it doesn't exist yet.
Yeah, you cycle through. There's a description what this configuration does. And once we're there, we have all to tell syslog-ng to log it by adding the below loghost.conf file. So source s_loghost, the filters that we defined, and the destination that we also talked about.
And then on the clients that you actually want to aggregate the logs from, they just need one line in their FreeBSD syslog.conf saying all the messages, send them over to this IP address. And they will. And then it'll be up to the rules on that IP address to filter out things they care about.
That's not too bad. And again, in next week's second part, we will cover a little bit more about this from the same blog. So in case you're curious, you can implement this now and just wait for next week's episode where we cover the rest. All right, then we have a heads up for you. There's changes coming in NetBSD. There is an entropy overhaul. And what's this about? This is on NetBSD current users.
This is Taylor R. Campbell saying, this week I committed an overhaul to the kernel entropy system. Please let me know if you observe any snags or issues. For the technical background, there's another thread, but the most visible user change or user visible change, you will get feedback about whether the bootloader or rc.d read the random seed, which is typically stored in var db entropy -file. In your D message, you will see entering seed from bootloader or no seed from bootloader. You can also query it after the fact with the rndctl-l command. The entry source called seed represents seed loaded either by the bootloader or from your RC scripts. You can see the diagnostic sections of the RND chapter 4 man page if you want to know more about how that works. If you're on x86, you can also specify the random seed with the type rnd seed and path, for example, in /boot.cfg. On ARM with EFI boot, you can specify it in the rnd seed EFI environment variable, which can be set with etc EFI boot.plist. Otherwise, rc.d will load it automatically, which much later than the bootloader can, from the random_seed file in your rc.d. So importantly, dev random no longer blocks repeatedly. It will block after boot until the system has full entropy, and then once that's done, it will never block again. This means applications that issue repeated reads from dev-random will no longer repeatedly hang. However, for the purposes of testing applications to make sure they have that behave sensibly in the event that dev-random does block, to simulate what would happen early in boot, you can re-enable the old behavior by setting kern.entropy.depletion equals 1, and it will cause the blocking for testing. You can also see a lot more zeros in the rndctl-l output than you used to. For example, on his T61P laptop, he shows the output from before and after. This does not mean the system has ceased to observe samples from these sources. Exactly the same data will be fed in by the drivers. At the moment, there is nothing that records the number of bits of data entered from each source, although you have a dtrace example to get some approximation. Rather, the numbers listed in rndctl are meant to be the upper bounds on the number of bits of entropy process that produce the data. But what does that mean? In the past, when the kernel took samples from devices not meant to be hardware random number generators, it would feed the samples into an extremely simple-minded model, a model that bears no relationship to the physical devices. To digitate a bonus fabulation of how much entropy is in the process that produced the data. In other words, the kernel was making things up and lying to you about the physical processes that it didn't know anything about. As part of this overhaul, I removed this dishonest fabulation. Only drivers for devices about which the unpredictability of the underlying physical process is known or advertised, generally just hardware random number generators, or the random seed stored on disk from the previous boot, will supply a non-zero entropy estimate. As the operator, you can instruct rndctl to disbelieve the entropy estimates for any particular device or type of device by using the capital E flag, or disabling collection of data altogether with the capital C flag. So in particular, they say you may find there are now more warnings about extracting entropy too early on some machines without hardware random number generators, for the same reasons that rndctl-l shows more zeros. The warning is rate limited and goes away as soon as the system deems itself to have reached full entropy. This is generally not a new deficiency, rather it's a new warning about an old deficiency that NetBSD and other systems like Linux have been silently or dishonestly hiding, or quietly leading to problems like they link to a website called factorable.net, which I think was the weak keys problem. So here are some workarounds. So for example, if you have a virtual machine, you may be able to enable the virtual hardware RNG. For instance, in QEMU, you can use the device VirtIO RNG PCI to attach a virtual hardware random number generator to pass entropy from the host into the guest via a virtual PCI device. NetBSD will automatically take advantage of that, although apparently NetBSD-current on ARM64 has a bug right now, leading to an interrupt storm at boot if you do this, but that should be fixed soon. If you're working on a modern x86 laptop or workstation that happens to have RD-RAND or RD-seed, and you want to install NetBSD on an appliance with no hardware RNG before you deploy it, you can run rndctl-S seed on your regular machine, and that will make a new file called seed that you can copy over to the appliance or whatever to give it a seed to start from. Then the rc.d script will take it from there.
Okay.
So that's some interesting changes.
Very nice change for NetBSD in the entropy area. We'll stay a little bit with NetBSD. In case you got curious how this all works, you can set up a NetBSD kernel development environment. This is what this article here is covering. And it's not too complicated, not too much, but still interesting. So the author here in this blog used t_pagefault's blog post as a reference for setting up my NetBSD kernel development environment, since his website is down. I'm putting down the steps here so it would be helpful for starters. So the overview of the setup is the following. They use a Linux host with QEMU target, then tracing and debugging using QEMU's built-in GDB server, a cron job with rsync to keep the files updated with host and guest, and package in for simplicity. Sometimes you have to use package add to get stuff done, but yeah, that's personal preference, I guess. So host configuration. Make sure you have the latest version of QEMU installed, as we will be using x86-64 NetBSD guests. We will need GDB that is configured with NetBSD x86-64 ABI. And so we need to compile it ourselves, and they provide instructions how to fetch that, extract the tarball basically, and change to directory, run a configure step, and then run a make job to install these. And then you should have it. Then building from NetBSD current. First step is to get the files. So you would create your own NetBSD directory or whatever you want to call it, then clone the NetBSD Git repository from GitHub and change into the source directory. And now for the time taking part, compiling the sources, then you run the build sh with the options for the architecture, AMD64, and a couple of directories that are all provided in the blog post here. And then they comment here that you can get some sleep. It'll take some time because it has to basically rebuild the whole system. But upon completion, the directories will have the following files: the cross-compilation toolchain in tooldir, and the bootable image in releasedir/images. Now, getting the guest up and running, you would run QEMU image, create your own NetBSD hard drive. 10 gigs is fairly enough. And then you run QEMU system-x86-64, provide a number of CPUs, the drive you want to have, of course, the one that you just created, and with a CD-ROM maybe, with a NetBSD ISO in it. And once you have that started, you go through the standard installation without necessary clutter, like X11 games, you can skip all that. Just for development, you can use the base system. Configure all the necessary things such as SSH, users, and a couple of other preferences. And once the installation is complete, you can stop the installation, or restart the QEMU system without the CD-ROM, because now you can boot from the virtual hard drive. That should drop you into a virtual machine instance, which is now your new development environment. And the last thing to do is installing package in. Once you're up and running, you better install package in. It makes package management easier, so they provide a couple of steps how that is done. I think we covered this in a couple episodes already, so this is fairly straightforward. If you don't remember, here are all the instructions on the blog post. You can just use and copy. Then you use a text editor of your choice and fiddle with configurations. So you can say, of course, make options debug -G, so you can get the full symbol table for CTF, for example. So that helps debugging if you have the actual debugging symbols available. And then again, there's a big compile job left with build.sh. And again, this should luckily complete fairly quickly. And now you can SCP the files to the VM and replace the old kernel. And they show how to do that. And to debug with GDB, they also give a couple of instructions how to use the TCP port 1234 to do that. And then you have it. You can start debugging your NetBSD kernel. You can rebuild the system or the kernel bits that you are currently working on. And then you have your nice little virtual machine with a NetBSD development environment.
We've covered it before, but on Marius's blog, which there's a link to from the first story in today's show, there's also an example of how to do this with Beehive and NFS boot on FreeBSD, which has a really nice advantage of, if you're compiling your kernel on your host and then being able to make install kernel dester equals some directory you're sharing with NFS, it makes it much quicker to update the kernel in the VM and reboot, since you don't have to launch the VM and do an install off the CD, or especially, if the kernel panics at boot, you don't need to figure out some way to boot an alternate kernel or something in the VM when you can just overwrite the kernel with a different one. And it can make debugging much more quick, especially the iteration as you go through trying over and over again.
Oh yeah, that's good to know. All right, it's time for the Beastie Bits this week. There is an info from Dragonfly BSD that you can now use compiler cache to speed up desynth even more.
Yeah, so Ccache basically allows you to cache compilation units when you're compiling stuff. For example, Poudre on FreeBSD, you can use it so that if you're compiling multiple package sets, so the same packages but with different options a couple times or something, you can end up caching a lot of that and speeding up a lot. And it has good detection for what's changed, so it doesn't mess you up. And yeah, so having that in decent will be a nice advantage for them.
Oh, yeah. Then we have news from NetBSD. They have improved liboss audio and the future of OSS in NetBSD.
So this is a post from Nihilair, and they say there's two ways user applications can communicate with the kernel audio layer in NetBSD. The first is the audio interface, the native API based on the old Sun API with a number of very useful NetBSD extensions, or the OSS audio interface, a translation layer providing approximate compatibility with OSS v4's ioctls that are supported on FreeBSD Solaris and popular in the past on Linux, although less so. Linux drifted away from OSS and towards ALSA due to licensing disagreements, and then from ALSA to Pulse or to Jack and then Pulse, and who knows, his audio is weird. Because of this drift, we're seeing increasing problems with the OSS adoption today, even if the licensing concerns are no longer relevant, and other implementations of OSS have surpassed the original Linux OSS v3 implementation as far as the feature set and usability are concerned. So in NetBSD, it is recommended to use the native API for new code and only rely on the OSS layer for compatibility with existing code. I spent a while working on third-party software to improve support for the native NetBSD audio interface, including Firefox, SDL, which is a library used to build a lot of graphical applications, Port Audio, and FFmpeg. However, I've turned my attention to the OSS translation layer. Since a lot of older and less popular software still relies on it, I wanted to go over the OSS v4 specification and iron out any surprising differences. So in particular, looking at, for example, Audacity, which is what we're using to record this show right now. I should note that most of these fixes were to enable Audacity to work without patching. Audacity is interesting because it hits a lot of edge cases as far as the OSS API is concerned. Once I fixed the most notable issues, I made sure Audacity also supports the native API, writing the necessary port audio glue for Sun and NetBSD audio, and implementing those fixes took about 2 days. Then they have a list of the different incompatibilities. For example, the sound control DSP speed ioctl. The NetBSD 9 kernel supports sample rates up to 192 kilohertz. Specifying anything higher, and NetBSD's audio API returns an error code and keeps the sample rate at its original value, or the legacy default of 8 kilohertz, which is not particularly useful with modern devices. However, OSS applications expected setting the sample rate to always succeed, and the specifications state that the actual set sample value may be an approximation and will not always be the exact requested value. So if the requested value is out of range, NetBSD will return as if the call succeeded and set the sample rate to the current hardware rate, which is usually 48 kilohertz, setting the number of channels and triggers and the player volume and so on. And then in the future of liboss audio on NetBSD, hopefully after my changes, OSS compatibility is in a much better shape when dealing with unusual parameters and uncommon API usage. The quality of the code has also improved in the process of this work. Max V pointed me towards relevant or related information in the Linux OSS v3 compatibility layer in the kernel, and I was able to deal with it properly after looking at the OSS specifications. All of these fixes should be pulled up into the 9 stable branch of NetBSD. However, I personally like to eventually reach a point where we no longer need liboss audio. I've been writing a lot of code towards this goal. In many cases, the applications relying on it could be easily modified or told to use libao or SDL2 or port audio or OpenAL or one of the other abstractions instead, which already have native NetBSD audio support, so that you don't have to add native NetBSD audio support to every application if they use one of the common frameworks. But OSS aside, we'll probably need to start thinking about supporting 24-bit PCM in the kernel, since I've found a few audio players that don't handle making the samples 32-bit before writing them to the device. The Sun audio implementation in Solaris has supported this for a long time now, so maybe NetBSD can catch up.
So we'll see a little bit more coming down the line on NetBSD in the audio area. And then we'll jump back to Dragonfly BSD because they imported DHCP CD 9.02. A couple of the following changes. They have control sockets now are not opened in test mode. Privilege separation no longer aborts if the protocol is not available. For INET 6, they don't regenerate the temporary addresses without a state. They also reduce the RA log spam for INET 6. And DHCP6, they don't lock when things consistently fail. Well, that's good. INET6 also has added temporary directives to SLAAC options, and they ensure current interface flags persist when setting a flag, as well as DHCP via BPF is now aligned correctly. The CMSG buffers are also now aligned correctly. This is the alignment change. And host names are no longer clobbered when being forced, and router advertisement is received. There's a footnote. DHCP-D no longer looks at any possible kernel settings when deciding to manage IPv6 temporary addresses or not. You now instruct DHCP-CD to do this in dhcp-cd.conf. Playing whack-a-mole with various kernel knobs wasn't fun, and some operating systems have or are removing router advertisement, and thus temporary address management from the kernel, so said knobs are no longer there.
Yeah, I know there's been some discussion about using DHCP-CD in FreeBSD as well. There's some look at getting it capsicumized so that it can be in the base system. So it'll be interesting. I think, yeah, the biggest thing that stands out when you're looking at the diff stat is that the specialization for BSDs went down by a lot. There's a lot more minus signs than plus signs. So the code has definitely been simplified a bit by not having to look at each different BSD and how it handled the router advertisement stuff, and instead just make it a config setting.
And then we have a little reminder for you. You should watch this space for upcoming FreeBSD Office Hour. The next one is scheduled for May 13th at 2 p.m. Eastern, 1800 UTC. And you can find all of them on wiki.freebsd.org/office hours.
Yes, so the two I hosted are there. And we're also looking for more people to host. So if you're interested in running one on a topic or something, that'd be great. I know Dan's pretty busy finishing organizing the virtual BSD can and so on. So we'll probably put off him doing a Pudra one till a bit later. But we'd love to see one about a more in-depth version of that NetBSD development environment thing that we talked about today in the show, a FreeBSD version of that. We should get Tom Jones to do. He did a blog post about his dev environment a while ago. He could give some good tips about that and answer some people's questions. Or having one on ports and just having a bunch of port maintainers or committers talking about stuff. And we can make Benedict do one about docs someday.
Oh, yeah. Why not?
The goal is definitely not for me to have to host them all.
Yeah. So yeah, drop in at that time and ask a question, and then you get the direct feedback from developers. Or, hey, there's this bug report I have not yet heard about.
It can be anything from just bringing attention to a bug or a patch that you have, or asking questions, or whatever. It's just having a set time where you can maybe get someone that might know the answer or might be able to direct you in the right direction, and being able to have a bit of an interactive conversation with them in public for the benefit of everyone, not just whereas some of these people you can just ask them on IRC and that's great, but it's a little harder when you don't know them, and this is a time where they're specifically open to just being bombarded by questions from random people on the internet. And we make it available to everyone so that it saves us a lot of time by not answering the same question as many times, because everybody can watch the videos.
All right, it's time for feedback and questions. This week, we have 3 people, but we always love to get more feedback or questions in this segment. If you have any of those, send it to feedback@bsdnow.tv, and then we'll have future content for this part of the show. The first one that we have this week is Ghislaine with a ZFS question. Excellent. Here we go. I'm sure you are longing for a ZFS question, so here it is. I have 4 spinning Rust disk and 2 little 240 GO SSDs. This server will host several LAMP or FAMP guests running Linux plus LXD or FreeBSD plus Beehive guests. To have the best performance while having failure on one disk-proof system, should I use one SSD for log, one SSD for cache, or the Rust for data? Use the 2 SSDs in RAID 1 and 1.5 for the log, or 1.5 for L2ARC cache, or will the L2ARC and ZIL log compete for the I/O and therefore slow things down? He understands that the ZIL is for writes and L2ARC more for reads, but you have to write to the cache to start with. So also, will the write to the L2ARC also write to the ZIL doing double writes. I wonder what could be the best use of those 2 bonus SSDs.
Raiding together the 2 SSDs and then using half probably doesn't make sense. Ideally, you do want to raid to mirror the ZIL, because obviously if the SSD holding your ZIL fails, then that data that hasn't flushed yet is gone, and that's bad. For the L2 ARC, you don't want to mirror them because storing 2 copies of a cache doesn't make any sense. You're just going to wear the SSDs out faster. So you can partition them. Definitely wouldn't do half. The log device never needs to be more than like 12 or 20 gigabytes. So, I might do 8 or 12 or something like that off the beginning of each of those 2 drives and mirror it to make a log device, and then not mirror the rest of the 2 SSDs as an L2 ARC. But you're right. The writes to the L2 ARC will then be competing for bandwidth with your log device, and that won't help. Also, if you're just doing a web server, you probably don't have that many synchronous writes to need a log device. Currently, in this situation, your best bet might be to just have 2 separate pools, one of the hard drives and one of the SSDs, and just put the files you really care about being fast on those SSDs.
Oh yeah, that works fine.
The other option is there's a feature coming. It's in FreeBSD head, but it was not in a release yet, called Special VDEVs. This would allow you to, instead of using it as a log or an L2 ARC, you can use it as a metadata device. So you can mirror those 2 SSDs and have ZFS store metadata and maybe even small files. So any records that are, say, less than 8 kilobytes will get written to the mirror of the 2 SSDs. And then all your big data, like your 128K or 1 meg blocks of files, will get written to the regular hard drives. And this can make things faster in a way that makes more sense than possibly the L2 ARC. Because if you don't have a lot of RAM, an L2 ARC probably doesn't make much sense. And if you don't have a lot of things like database servers running, then a slog doesn't really help much. And if you do have a database, maybe it makes more sense to have 2 pools and put the database server, or at least, the var db mysql or whatever directory you're storing the data from the database in, as coming off the SSDs in its pool, and have the, the web server files, like the HTML files and so on, can be on the hard drive, because the popular ones will be cached by the ARC. And then your database will be faster than if you just have it on the spinning disk with a slog and an L2 ARC on the SSD, whereas your database is just always on SSD. It'll probably be faster. So that's what mine looks like. Basically, I have a jail or a VM or whatever for the web servers and a different one for the database server, although that you can do it in the same one because it's just different directories. Or even, in a Beehive guest, just connect 2 disks, one that's backed by the hard drives, and that's where the OS and the web server and all that is, and then a separate drive that's backed by SSDs, and that's where you keep the database. And then in your VM there, you'll have the speed of SSDs for your database and anything that needs the speed, and the bulk storage capacity of your spinning drives for the rest.
Yeah, so try this configuration and maybe send us a follow-up with maybe some performance numbers or some things that you experienced running this setup. So that will be probably interesting to other people as well. Okay, so thanks for that question. Next up is Jake with a question about PayPal donations or feedback. Jake writes, "Hi guys, thanks for always for the show." Yeah, you're welcome. I've noticed that when I pay for something with PayPal, they ask if I want to donate $1 to the FreeBSD Foundation. I do. Does that get counted as an individual donation, or does it look like one big donation? I'm thinking about the 501c3 public good situation. Thanks again, Jake. So first of all, thanks for your donation. I think internally, when we process that, since this is one income from like the source, in this case, PayPal's...
Well, I think even just for privacy reasons, PayPal definitely doesn't tell the foundation the name of everybody that donated. And the same for I think it's the Amazon Smile, where you can donate a portion of what you buy on Amazon.
So they collect all that and give us one, I think, monthly or...
One payment, yes. But I don't know if they tell you with that, this was from this many... I guess even for Amazon, it's probably this many orders, not this many unique people.
Yeah, just from this program, you received this amount of money, dear donation, dear foundation.
And possibly, it was from, X hundred orders, but it doesn't give you that much detail. but it definitely helps. It still looks good in the public good situation, so I think it's fine. We're not really out to game the system by getting as many separate $1 donations as we can.
Yeah. If you really want to have an individual donation, then you go to the websites directly and donate there. And you can also have a special dedication or in memory of something. So that's a bit more configurable, if you want to call it that. But definitely thanks. Even small donations are helpful to these foundations. And they go a long way of supporting the development and other things around the BSD project, or in this case, the FreeBSD project. But the other BSD foundations are very similar. Okay, and then we have Oswin with a Hammer tutorial. Oswin writes, "Hello, you had a really good course for BSD Hammer, but now when I try to have a look at that, I get a page 404. Not found. Yeah, this was the URL, so this is one of our old tutorials from the very, very beginning when even I wasn't on the show."
Yes, so when we migrated the website to the podcast platform Fireside, we didn't carry that over. I have the tutorial still, and I will try to find time to get all those tutorials reposted on the website. I'd also like to just get, I think Fireside doesn't have the first couple hundred episodes. They just have what was in the RSS feed when we migrated over or whatever. So it's only got the last 100 episodes or something. And I'd like to have all of them. Although I got to figure out a way to make it happen without pushing all those like 5-year-old episodes into people's RSS feeds.
Hey, there's new content, a lot of it, all of a sudden. I guess this was also Hammer 1 at that time, so there might be some changes coming down or have already come down the line, so that might not apply anymore, the tutorial.
Yes, Hammer 2 is a bunch different. So if somebody wants to write a new Hammer tutorial, that'd be even better.
Otherwise, check out Dragonfly BSD's homepage. They surely have the documentation how to run a Hammer. Or other people who have more current tutorials about Hammer and setting that up, they could definitely send that to us, and we'll cover it either in the show segments or as a follow-up to this feedback. But definitely, thanks for your caring about these old tutorials. It's definitely good that people refer back to them. Thanks for that. And I think that pretty much wraps up this episode. Thanks for listening in. Hope you stay indoors just a little bit longer. And then we'll have you listening to us next week again.